Positional Variance Profiles, a new take on the speed-accuracy trade-off by Julien Gori and Quentin Bellut from Sorbonne University. Fitz's model and experiments are the go-to studies for the speed-accuracy trade-off in HCI. In a Fitz law experiment, the task is a time minimization task. Accuracy is determined by a target of given width, and the participant has to hit the target as fast as possible. There are two versions of the law, the nominal, which uses W, and the effective law, which replaces W by the observed spread sigma. Fitz's model is for endpoints only and says nothing about trajectories. We recently proposed an alternative to Fitz's law called PVPs. We'll start by reviewing PVPs and explain how the present work is positioned. Now, the model applies to time minimization tasks that we have just seen, as well as dual-minimization tasks where the participant aims towards a line at a given distance and has to jointly optimize movement time and precision. If we get a participant to perform some movements in either task for a given condition and synchronize all trajectories, we get a plot like the one on the left, which represents position of the cursor against time. Now, if we compute the variance of these signals against time, we obtain a profile like the one on the right with two phases. A first variance increasing phase with a small duration, and a much longer second phase where variance decreases steadily. In our previous work, we evaluated the features of these profiles on two datasets. What we found is that the duration of the first phase was about 200 to 250 milliseconds with a small effect of distance. The distance covered during the first phase was about 2/3 of the total distance to target, and the standard deviation at the end of the first phase was proportional to the distance to target. For the second phase, we produced a theoretical model which namely predicted that the standard deviation of the trajectories decreases at best exponentially over time at rate c, which also means that the logarithm of the standard deviation decreases linearly in time. This property is illustrated in the plots, which all have a log scale on the y-axis. On the left panel, there are 8 variance profiles that correspond to a time minimization task for various values of d and w. On the middle panel, there are 5 variance profiles obtained during a dual minimization task for various strategies, from extreme emphasis on speed to extreme emphasis on accuracy. In both panels, the first phase is very short and has an almost constant duration. Then the second phase starts, and to reach a smaller width or accuracy constraint, you have to remain longer in the second phase, which results in this plateauing that is obvious, especially in the middle plot. The right panel shows how we estimate the slope of the second phase by fitting a spline model. The two-phase model also predicts Fitz's law, as movement time predicted by the model is just the sum of the two phases' duration. The model predicts the effective version of Fitz's law, and from there we can also express the nominal version. All terms in the intercepts are constant except for an alpha d term. Our model predicts what Guillard calls the weak version of Fitz's law, where the slope does not depend on d and w, but the intercept does. The value of alpha depends on the device and may be smaller. In comparison to experiments based on Fitz's model, PVPs have several advantages. They describe whole trajectories and can be applied in tasks where w is not defined, whereas Fitz's law is a model for endpoints that is applied to time minimization protocols. To evaluate Fitz's law parameters, you have to precisely determine the end of movements and have several values of d and w. Here, a single condition that emphasizes accuracy is needed, and movement don't even need to fully terminate for the model to be fit. Further, we can better interpret the model parameters. In the paper, the first thing we do is provide an extension to 2D, because the 2D version is needed in HCI. We also replicate our original findings, but using more values of d, because the dataset that we use only had 2 values of d, and more devices. We also address some problems with Fitz's law that we did not touch upon in our previous work. We also present a Python library that is easy to use so that people can engage with PVPs. To extend the PVP formulation, our strategy is to find a 1D proxy of the spread of the data and apply the regular PVP method to it. The first step is to project all movements in a basis relative to the target and the starting point. Alpha is the projection in the direction of the target and beta the direction orthogonal to it. Then we compute the covariance matrix of the alpha-beta vector at each timestamp. The covariance matrix is the generalization of variance to n dimensions, and it can be estimated by the sample covariance. Then we reduce the covariance matrix to a single term. There are infinitely many ways to do so, and we consider here 3 that are interesting. PVP alpha, where we select the variance relative to the principal direction of movement, PVP total, which sums contribution from both directions, but no cross terms, and PVP generalized, which takes all terms into account. For PVP alpha, the idea is actually to consider only deviations in the principal direction of the target, and this is something that the This is actually the ISO recommendation for Fitts law for the endpoint case. For PVP total, we used actually the so-called formula for total variation, which generalizes as the square root of the trace of the covariance matrix. And in the endpoint case, it is actually equivalent to what Warlock and colleagues called the distance from centroid formula. For the generalized version of PVPs, we use the so-called Wilks generalized variance, which generalizes to the 2nth root of the determinant of the covariance matrix. Total and Wilks variance have interesting interpretations, which I cannot discuss here. We then performed an experiment to evaluate the three PVPs on the time and dual minimization paradigms with three different devices, a mouse with acceleration, touchpad, and a controller, and 6 different values of D. Because we had a within subject design to keep experiment duration low, we did not fully cross D and W in the time minimization condition, and there are more details about this in the paper. Now, the first result is that we found very little differences between the three PVPs. You see that PVP alpha, which is the blue one, kind of sits in between the two others. This is something that we actually prove in the paper, and the differences here are small because the variance in the beta direction is always rather small. So in the remainder, we only present results for PVP alpha. We now come to the effects of D on PVP features. So on the left, we have tau, the duration of the first phase, against D, and you see for the mouse and the touchpad, in blue and green, tau is almost constant, whereas for the controller in orange, you see that tau scales a bit with D. So that suggests a weak version of Fitts law for the controller and a strong version of Fitts law for the other two devices. On the right, you see d tau, the distance covered during the first phase, and it's proportional to D. For sigma 0, which is the variance at the end of the first phase, we see that the linear relation seems to hold as well. And on the right, C seems constant as the model predicts. So to quantify these results, we fitted multi-level linear models to PVP features guided by the previous box plots. And multi-level models are similar to ANOVAs, but for the case of regression of continuous variables on the ratio scale. So for a bit of explanation, in the first model for tau here, D star W means we look at effects of D, W, and their interaction. The one bar participant allows each participant to have its own intercept, similar to what you would do in a repeated measures ANOVA. And other simple effects like device means that each device has its own intercept contribution, and interaction effects like device D allows different slopes per device for the model. We replicated the results from our previous study, but it is much more convincing now because we have more levels of D. The third result is about Fitts law predictions. Namely, we can compute the values of A and B and see how well they match to the one that results from directly fitting Fitts law. So here there's in bold the estimates of B, of effective A, and nominal A. And so overall estimates are pretty accurate except for the controller. In the paper, we also discuss a few implications for Fitts law. First of all, we highlight the arbitrary nature of the ISO recommendations that form the standard for Fitts law evaluation. In particular, the 4.133 constant could be anything else. Second, negative intercepts are actually possible. They are not just some constant positive term, which in our model is tau 0, but it also accounts for error rates in the nominal case, for scaling effects via alpha and gamma. And because of the logarithm, all of this can become negative. There are more implications in the paper. Finally, we have released a Python library for PVPs so that the community can use them more easily. The library is on PyPy, the package index of Python, and can be easily installed. It has a documentation and can be used very easily. So this is an example code snippet. So usually you would create a PVP object, so here PVP alpha, and then you would loop over some data set to add trajectories. Once all the trajectories for a given block have been added, you can simply compute the profiles, plot the profiles if you want them, and then plot the fitted profiles with. So the conclusion is that PVPs are an alternative to Fitts law evaluations. The protocol is it's much simpler than the protocol is simple. Aiming at a very small target is enough, and there's no need to cross D and W. There's also no need to precisely determine the end of a movement, and we get more information than just A and B. We show that it can extend to any dimension, and there's a library available for this. Well, thank you for your attention.